Okay, this video is Unit 11C, looking at proportions and the golden ratio. So 11B, we are looking at the ideas of symmetry and perspective. Now in this lesson, we're going to kind of look more at the idea of proportions. And there's a quote here from Kepler in regards to he's an astronomer in regards to the importance of proportions. It says geometry has two great treasures. One is the theorem of Pythagoras, the Pythagorean theorem. The other is the division of a line into extreme and mean ratio. The first we may compare to gold. The second we may name a precious jewel. So a lot of mathematicians really enjoy this, the concept of geometry, and we're going to be talking about this idea called a golden ratio. But Kepler's statement about the division of a line into extreme and mean ratio describes one of the oldest principles of proportion. Dates way back in the time of Pythagoras, when scholars asked the following question. So how can a line segment be divided into two pieces that have the most appeal and balance? So it's the most aesthetically pleasing and the most balanced. Okay. Now, although this, this was a question of beauty, there seemed to be some general agreement on the answer. So here it's kind of their thought process. Suppose a line segment is divided into two pieces. So as you can see down here in this figure right here on the right, 1137, divided into two pieces. We call the length of the long piece L and the length of the short piece 1. And the Greeks claimed that the most visually pleasing division of the line had the following property for the ratio of its lengths: that the longest piece, L, to the shortest piece is the ratio of the entire segment to the long piece. So L divided by 1 equals the whole piece, which is L plus 1 divided by L. And this is how we come up with the golden ratio. And so what we're going to do real fast here before I talk more about the golden ratio and where this comes from, we're just going to look at this equation. L over 1 equals L plus 1 over L. If we were to just go ahead and solve this equation for the value of L, okay, what I would do is cross multiply here, so you get L times L, which is L squared, equals 1 times L plus 1, which is just L plus 1. And then I've now got a quadratic equation, so I'm going to subtract L and subtract 1 to set it equal to 0. So this gives me, in the quadratic formula, this gives me the value of A equals 1, B equals -1, C equals -1 when we're looking at the quadratic formula. Or quadratic equation. So then for the solution to the quadratic would be the opposite of b plus or minus the square root of b squared minus 4 times a times c, all of that divided by 2 times a. So this is going to be the opposite of -1 is 1, plus or minus the square root inside there. -1 squared is 1. And then -4 times 1 times -1 is plus 4 over 2 times 1, which is 2. So I get 1 plus or minus the square root of 5 over 2. And that's the value, again, of L. That's what L is equal to. So this number right here, and the 1 minus the square root of 5 over 2 is a negative. So for the golden ratio, we just use 1 plus the square root of 5 over 2, which is approximately 1.6118. It's an irrational number. It goes on forever. But that value is known as phi, which is just a Greek letter, and it is the golden ratio. So L, when you take a line segment and you break it into two pieces, and one part is 1 unit long, then L is approximately 1.618. And that is this idea of the golden ratio, and it's one of the most aesthetically pleasing to the eye ratios that exist. And there are many things in architecture an ancient architecture that follow this. So again, that number phi is commonly called the golden ratio. Sometimes you'll hear the golden mean, the golden section, or the divine proportion, but I'll stick with the golden ratio. And it is an irrational number, often approximated as 1.6 or 8/5, but again, we can get much more accurate than that, 1 plus the square root of 5 divided by 2. And so what we can do is, for any line segment divided into two pieces according to the golden ratio, the ratio of the long piece to the short piece is the following. We get, if the long piece is x and the short piece is y, that ratio is equal to the golden ratio divided by 1. So, here's your golden ratio in 1. So x and y could be different values, but we get this relationship here. So you might think of it as long over short equals, and the golden ratio divided by 1 is just the golden ratio phi. So we get this proportion. The long side divided by the short side equals the golden ratio. And then we can say, well, if we know the long side is a certain amount, how long should the short side be in order for it to match up with that golden ratio? So let's look at this question number 12 here. We have a line subdivided according to the golden ratio with the smaller piece having a length of 5 meters. What is the length of the entire line? So we know that the small or the short is 5. So we would say the long divided by 5 equals our golden ratio. I'll just use 1.618. So the long, if I times both sides by 5, the long here is going to be about 8.1 when I round to the nearest tenth. So the total length is going to equal 5 plus 8.1, or 13.1, and this is in meters. So 13.1 meters is the length there. But if we were looking and drawing this out, then if the small side is 5, this longer side, for it to be a golden ratio, then it would be 8.1, and then the total length would be 13.5. So that's how you could find the long side and the full length if you're just given the short side and you know that it follows the golden ratio. Okay, now we're going to look in this next problem. So consider the following lengths of one side of a golden rectangle. So get a golden rectangle would be it's not going to be a rectangle, my bad. But a golden rectangle is where you have one side length is L, the other side length is 1, and that relationship, that ratio is, if you take L over 1, that ratio is phi. And so if it says if one side is 5.8 meters, find the length of the other side. Now notice that 5.8 could be the short or it could be the long side. And we're going to use phi equals 1.62 in our work here. So, if 5.8 is the long side, then remember our ratio would be the long, which is 5.8, divided by the short, equals phi, which is 1.62. So then, if this is the case, I would times both sides by the short side. So 5.8 equals 1.62 times the short side, and then I would divide by 1.62. So I get 5.8 over 1.62 is equal to the short side. And if I take 5.8 divided by 1.62, I would get that the short side is about 3.58 meters. So if the long is 5.8, then the short is going to be approximately 3.58. Now, if we switch gears and we say, okay, if 5.8 is the short side, then we'd have the ratio long divided by the short, which is 5.8, equals phi. So we times both sides by 5.8, and you get that the long side is approximately 9.40, and again, this is in meters. So if you're given one side or one part of this golden ratio and you need to find the other, there are two possibilities, because you don't know. In this case, we were just given 5.8 meters. We didn't know if that was the long or the short side, and so we just make the assumption, well, if it's the long, then we get 3.58. If it's the short, then the long side's got to be 9.40. And that's how we can use this golden ratio to find missing sides of a rectangle or missing lengths of a line segment. When we know that that golden ratio is always about 1.62 or 1.618 is one that was commonly used when I was going through my math courses. But anyway, it's just an interesting thing about the golden ratio. And again, if you look into the history, your textbook has a lot of historical buildings and art that follow this, and it is the most aesthetically pleasing ratio that's out there, and it's been around for a long time. So that'll end part 1, and then we'll look at about the golden ratio in nature and a couple other things.